Let's do some examples of computing limits for functions of multiple variables. Our first one is 5x squared y divided by x squared plus y squared. And we're taking the limit as xy approaches the value or the ordered pair 1, 2. So let's follow our first rule, which is just trying to plug it in. So we don't notice any immediate issues because we're not dividing by 0 or anything of the sort. So the top is 10, the bottom is 5. Our result is 2. So fairly straightforward. We like that. Let's take a look at this one. We have xy approaching 0, 0. So if I were to plug 0 directly in, I get 0 squared, which is 0, minus 0, divided by 0 plus 0. So I'd have that 0 over 0. And that's a problem. That's an indeterminate form. The issue is we don't have access to theorems kind of like L'Hopital's rule, specifically because in L'Hopital's rule you were defining a derivative with respect to one variable, and we don't really know what a derivative means for these types of problems, so we need to be a little more clever with our algebra. So if I think about what this input is, sometimes it's helpful to define a path where one of the variables equals another variable. So what am I saying? I'm saying, like, what about the path where y equals x along that path? So essentially, if the point's the origin, I'm going to follow a path from 10, 10, 9, 9, 8, 8, 7, 7, 6, 6, and I keep going till I get to 0, 0. If I were to do that, that would give me x squared minus x squared over x squared plus x squared, which is 0 over 2x squared, which is 0. So you might say to yourself, okay, the limit is 0. But then you have to think, okay, well, that's one path. What about for other paths? So specifically, what about a path where instead of y equals x, we think of y equals mx for any slope? So if we're going to plug that in, that becomes x squared minus mx squared over x squared plus mx squared. So a little bit of algebra, we can multiply that out. Now what we see is there's an x squared in common on top and bottom. So what we find is 1 minus m squared and 1 plus m, 1 minus m squared on top, 1 plus m squared on bottom. Now, if m were equal to 1, we would have this case, and that would just be 1 minus 1, we'd have 0. But what about the case where m equals 2? We end up with negative 3/5. So what you find is that even though along that path y equals x, the limit is 0, along the path y equals 2x, the limit is actually negative 3/5. And it's similar to the way we did it in introductory calculus. Remember, if the left and right hand limits didn't agree, then the limit didn't exist. And similarly, if we take two paths that both take us to the same final point, but along the paths the limit is different, we know the limit does not exist. So D and E does not exist. Finally, we have this piece. xy goes to 0, 0. Now, if I plug that in, notice that's the same piece as here, so I could try to plug it in. I'd get 5 times 0 times 0, so 0 on top, 0 plus 0, I'd have 0 on bottom. And I could try a parameterized path, and that would yield some information about what we can do. But it may not give us exactly what we're looking for. So what I'm going to do is I'm actually going to use a coordinate transform. I'm going to say, in general, I know that x is r cosine theta and y is r sine theta. And so that's okay. All right. So why do that? Well, let's sub that in. We end up with 5 r cosine theta squared, r sine theta, all over. Now, remember the relationship is that x squared plus y squared equals r squared, right? Remember that? So we would have 5, not 5. You just have r squared on the bottom. And then you'd have 5r cubed cosine squared theta sine theta all over r squared, which then becomes 5r cosine squared theta sine of theta. Okay, well, you might say that, great. Now, how does this help? Well, it helps because if you think about the fact that xy is going to 0, 0, then what you know is that r is actually shrinking to 0. The r has to be shrinking to 0. There's no way around it. If xy goes to 0, r goes to 0. But then you might say, okay, well, what about the paths? What about the paths for all the thetas and stuff? And that matters. That matters. But we can be a little clever with what we know. If we think about the graphs of cosine and then the graphs of, of sine, there's an interesting piece. They're always between 1 and -1, which tells me that the absolute value of sine theta is less than 1, and the absolute value of cosine theta is less than 1. So if I think of this as its absolute value, then I know that it has to be less than or equal to 5r. But we know that the limit as xy goes to 0, 0 means r has to go to 0. So what we're really doing is we're taking the limit as r goes to 0 of 5r, which is 0. And you might say, well, where can the absolute value come from? Well, there's another trick that you might have learned in introductory calculus, which is that if you want to show that the limit of something is going to 0, you can show that its absolute value goes to 0, right? Because it doesn't matter if it's negative or positive. If the absolute value goes to 0, it compresses in. So this one, again, required a little bit of cleverness, required some transformations. There's other ways to do this. There's ways that involve algebra that relate these concepts together to show you that that does in fact go to 0. But it's each particular way you try to do it is going to involve some cleverness. And so you have to play around with some of these to try to stretch yourself to see if you can understand the best way to approach these problems.